Okay, thank you very much for attending this talk. So in this talk, I'm going to cover basically the recent work from our group. We basically designed an efficient architecture for long video understanding. So the title of this talk is called Vamba, Understanding Hour-Long Videos with Hybrid Mamba-Transformers. So a bit of the background for this talk. So we know that long video understanding is a very important real-world task that has a lot of real-world applications. For example, we might want to detect anomaly actions in a continuous surveillance video stream. We might want to basically control the autonomous vehicles based on the cameras from the camera that capture from the cars. We also have a lot of the online resources about procedure videos and instructional videos, and people might frequently go checking out those videos and then pretty much learn from those videos. And we might want to have a summarization for the main contents of these videos, and also some of the users might ask for specific questions regarding the videos at a specific moment. So usually these tasks cannot be solved by only looking at a few frames. So for example, we have an example here of a cooking video, like a tutorial. And we see that after, for example, we're very interested in the question of before we cook the bacon, what kind of ingredient we want to add into the pan, basically. So, and we can find from the video that the captions that it's about adding oil to the pan and spread it well so that it prepares to cook the bacons. But if we only, for example, sample like 8 frames, 16 frames from this video, the video could be a few minutes long, or it could be even a few hours long, then it is very likely that we're just going to simply miss the intervals that indicates those moments. So usually, it's going to be important for this task that we perform a dense sampling. For example, sampling several hundreds of frames or even several thousands of frames, such that we can include those information, the relevant information, into the model, as the input to the model. So we are interested in one specific type of model for solving this kind of problem, which is the large multimodal models. So it's something similar to a language model. You might have used, for example, ChatGPT, GPT-4o, and you can, for example, input an image and you ask some questions about this image. So that's what we call the large multimodal models, because it takes multiple different modalities. It can take images, videos, and also text as input. And the way that a typical paradigm that these large multimodal model works is that they basically use a vision encoder to translate the video tokens into, translate the video input into a series of tokens. And then they combine these video tokens with the text tokens together, and then they input combine this big sequence of tokens into a LLM decoder to generate text responses. And one important characteristic of these models is that most popular and also most powerful models of these LMMs are based on transformers. And by saying transformers, we mean both the vision encoder and the LLM decoder. So you can think of the blue part as a small transformer, and then you can think of the yellow part as a big transformer. There are several open source models that have been very popular. For example, the Queen 2.5 VL, the Intern VL3 models. They are all based on these common architecture. So one central question around the transformer model is the quadratic complexity with respect to the number of input tokens for self-attention layers. And this has been like a problem that people have been like putting extensive efforts on for different research. And then if we express this in a more mathematical form, we assume we have n video tokens and n text tokens. So the combined sequence will have n plus n tokens. So we'll have a time complexity of big O, d times n plus n squared. So d here is the dimension of the transformers. So you can see the square sign there, which means it's actually blocked by, I think it's a failure of a screen, but it just means that the quadratic complexity with respect to the input number of tokens. And the memory complexity also quadratic to the total sequence length. So usually, and recall that we mentioned earlier that we need hundreds of or even thousands of frames for long video understanding. So this translates to a very long sequence of video tokens. So n could be in the range of 50K to 100K or even more. Because some of you might know that a vision encoder, it typically has a patch size of, for example, 14 or 16. So it translates the input into like several hundred tokens per frame based on the input resolution. So it adds up to like 50K or even 100K of tokens in total. And this gives a very high complexity to the total complexity based on these two formulas that we have mentioned before. On the other hand, we observed that there are relatively fewer input tokens on the text instructions because the instructions are usually simpler than the video contents. For example, we can have an instruction like, can you describe the video in detail? So this is only a couple of tokens, a few words. We can have at most, for example, a few hundreds of tokens, but that won't be very long compared to the vision tokens. And so in most of the cases, n will be much greater than n in the long video understanding problems. So the other thing that I wanted to mention is the inference for large multimodal models. And specifically, there are two stages in the inference for an LLM. The first stage is called the prefill stage, and the second stage is called the decode stage. So prefill stage means that we are prefilling all the instructions, including the videos and also the text instructions to the model. So these are the things that we already know that we are going to input into the model. So this includes like a video, several video frames, and also an instruction that includes a question, for example, that asking the model to generate a response. And the decode stage is for generating new responses, the new like tokens from the model for answering those user instructions. So the prefill stage involves using causal self-attention layers across the full input, the video and text token sequence, and which is the main compute bottleneck for long video models. For the decode stage, so let's say we have a language model, so just large language models. We can ask a very simple instruction. For example, we just ask the model to, can you write an academic paper for me? Right, so it will generate a title, an abstract, introduction, related work, and also probably a method section. So each of these sections will be containing a lot of tokens because there will be a lot of paragraphs. So you can find that for LLMs, there could be chances that the decoding stage is going to be more complicated than the pre-filling stage because we are going to generate more tokens compared to the tokens that we're going to input into the model. But for long video understanding models, because we mentioned that there is a very long sequence of video tokens as input, so the pre-filling stage is still going to be having a higher complexity compared to the decoding stage in most of the time. So our target in this paper is to design a new model that can enhance the efficiency of the pre-filling stage. Now, what kind of architecture can we looking at or can we employ in our models? So we turn to a specific type of architecture called Mamba, and then they are a type of structured space-based models so you can basically think of them as a recurrent sequence model. So they are kind of similar to RNNs or LSTMs in terms of the recurrent models. Which means that they have a few very nice properties. The first one is that they have linear complexity with respect to the input number of tokens. Because for an RNN model or a recurrent models, you can only generate an output based on the current input and the previous hidden states. You don't need to look at all the previous tokens as we did in the self-attention layers. Also, it means that we have constant memory complexity because we only need to store a hidden state that describes all the past history of the inputs. And this hidden state has like fixed dimension, and unlike transformer that they are scaled with respect to the number of input tokens. But what's different from between a Mamba model and an RNN model is that the Mamba models are specially designed to handle long context tags. So you can think of them as they have some specially designed components that handles long context tags better than the RNN models. So RNN models are known for they tend to forget things when there are the input sequence becomes very long. So they tend to forget the things from the beginning of the input. But the Mamba models are better at handling these type of tasks. So if you look at the two types of models, Mamba and transformers, we know that Mambas are efficient. They have linear complexity. They are good at handling long context tasks. But if you're only using Mamba models to build language models or multimodal language models, we haven't seen them as successful or as powerful as the transformer-based models. For transformers, we know that they are very powerful. They have been proven to be successful in multiple language and multimodal understanding tasks, but they suffer from the quadratic complexity that we mentioned before. So our intuition is, how about we combine these two together? How about we take the advantage from both type of the models and combine them together to get a new model that can handle the task really well, but also be very efficient. So because we know that the video tokens are having a very long sequence of tokens, so we are thinking that how about we use Mamba to handle the long sequence of video tokens. And also because we mentioned that the text tokens are not that long. They could be a few hundred tokens, but they will not be in a very long sequence. So we can still tolerate the complexity from the transformer models based on this not too long input. So we can still let the transformers to handle the text, which is in most of the cases not too long. So that's exactly what we did for Vamba. We have the red part is a transformer. This is kind of similar to a transformer part. It composes a self-attention and a cross-attention to handle the text tokens. And we have the blue part, which is the Mamba blocks for video tokens. I'm going to go into this in detail, but go into this in detail for a second. But I would first like to mention that why we like to design these models in this manner, like why we specifically want to use this kind of architecture to handle the two types of tokens. So our key intuition is that we have already known that transformers are very successful. They are very powerful in terms of handling multimodal content. And so therefore, we want to make our hybrid model behaves similarly to the transformer model. And here it means that given the same same set of inputs. We want the outputs to be as similar as possible to the transformer models. But also at the same time, because we are using a hybrid architecture, it also becomes more efficient. So our solution is that we first study how a transformer-based model updates the text and video tokens in each of these layers. So basically, we study how what the input to this layer looks like, and also what the outputs to these layers looks like. And then we try to design Vamba to approximate this update for text and video tokens. So this is like a side-by-side comparison between a standard transformer, a causal transformer, with Vamba on the left side. So basically, for every video, so these are like several equations. So I'm not going to very detailed explain those equations, but you can pretty much think of them as we have for every video tokens, we have the transformer model that is going to use the first equation to handle these video tokens. For Vamba, it's going to be the second equation. For every text tokens, the transformer is going to handle it using the third equation, and then for Vamba, it's going to be the fourth equation. So we're trying to make the output from equation 2 to be as similar as equation 1, and the output from equation 4 to be as similar as equation 3. So, and basically what we do this is by training the model on a large data set such that it learns the pattern and also aligns with the transformer models based on the input. So here, if you look at the transformer part of the model, we can find that it contains a self-attention layers and a cross-attention layer. So self-attention layer is actually exactly the same as you can see on the left side part for a vanilla transformer model, but we only restrict this self-attention model to self-attention layer to be only including tokens from the text tokens. So the text tokens are relatively there are not too much tokens in those text instructions, so we have a relatively higher efficiency. We also use a cross-attention layer to let the text tokens cross-attending to the video tokens, such that this part of the model, the complexity can also be maintained to a relatively lower like magnitude. So we're going to introduce them in a second. So if you look at the overall complexity of this model, for the Mamba part, we have a linear complexity with respect to the token sequence. So M here, remember, recall that it's for the total number of video tokens, and N is the total number of text tokens. So we find that the time complexity becomes big O V square M. So we get rid of the quadratic sign, the square sign from M, so it reduces the time complexity. For memory complexity, it's still constant because of the properties from Vamba. For text tokens, we have two parts, one cross-attention and one self-attention. For cross-attention, the complexity will be O M by N, and then the self-attention part is O N squared. So we still have an N squared here, but this N is going to be way smaller than M plus N, as we described earlier. So if we combine them together, we kind of reduce the complexity from M plus N squared to M times N plus N squared. And this is kind of like a near linear complexity with respect to with respect to M, which is the number of video tokens in the sequence. So this translates to a huge runtime efficiency improvement. So we tested, we kind of profiled the two models based on training efficiency and also inference efficiency. So for training, so the blue lines here all represents the transformer models, and the red lines here represents our model, the Vamba. So you can see that actually the first block is for memory comparison between training the two models. We find that the transformer models, they tends to running out of memory as the frame number increases to, for example, 128 during training. But for our model, we can increase it to at most 512. So that's like a 4-time improvement in terms of the context length that can be fitted into the model. For inference, it's like a similar trend. The transformer-based models can only handle 256 frames, but our model can handle up to 1,024 frames. We also computed the flops and also the runtime, the actual runtime in seconds during training and testing, and they also show like a consistent improvement compared to the transformer models. Now, I'm just going to show some results, some numbers comparing our models and the transformer models. So on the in the table, we find that the model actually performed quite well on several long video understanding benchmarks. So these benchmarks are related to videos with maybe 30 minutes to an hour of duration. So that's like very long video understanding. We call it hour-long video understanding because a lot of the videos are exceeding 1 hour. So we got pretty good scores compared to some previous models that are also trying to make the models to be more efficient, but they are still using a transformer-based architecture. If you look at the line plot, we find that our models, so our models on the top is like the orange curve. It scales more nicely with the, if we increase the number of input frames. So it kind of shows a consistent model performance improvement as the input frame scales up to 124. But for the other transformer-based models, they kind of decrease, the performance started to decrease after 512 frames. So these are basically more numbers. So I'm going to just skip that. Those are for benchmarks that are not that long, but also quite long, and also short video understanding benchmarks. Here are some kind of qualitative results from our model. And this figure here mainly shows that our model produces more accurate responses in terms of describing the video content compared to some other models. So here, for example, the second example, the question is kind of tricky because it involves describing a magic trick. And basically the magic trick is about a person is trying to creating an effect that a ring is going to pass through his finger. So the other models get confused, but our models basically can correctly describe this video. Here are more examples. I'm not sure if this is going to be large enough for the text to be like visible, but this is basically about describing providing a more comprehensive description of the video using a longer paragraph. And you can see that our models can generate these kind of longer text outputs without losing the accuracy of basically understanding the contents in the video. So lastly, I just wanted to mention that so Vamba, as part of the work, this is part of the work that we have been putting effort into long video understanding. So we are trying to improve this task from multiple perspectives. We aim to create better training data sets to train better models. We aim to create better evaluation benchmarks to more accurately evaluate the performance of those models. So there are several previous works. Vista is also a previous work done by our group, which has been accepted by CVPR 2025, and it is about generating high quality video instruction following data, which is the training data from the low quality video caption pairs. So this one actually has been employed by Hugging Face in their small VLM2 as part of the training data. Vamba is the one that we described in today's talk. We also recently released a benchmark called Video Eval Pro, which is a more robust long video understanding benchmark based on open-ended questions. So a lot of the questions that are that we show in this work, so these benchmarks, these numbers here, they are actually based on, for example, multiple choice questions. And then they have they tend to have a higher degree of variations in performance because model tends to guess. Sometimes they guess the correct answer based on the MCQ questions. So we are trying to make the benchmark more reliable and also harder by introducing these open-ended questions to the benchmark to more properly evaluate the models. So if you're interested in these two works, you can scan the QR code. And yeah, thank you very much for attending this talk. So also, if you're interested in the model and the code for this paper, you can scan this QR code. And any questions are welcome.
Thank you for the great session. How does Vamba currently handle, let's say, something similar to object tracking? Let's say there are 10 people in a retail store video, and one of them is shoplifting, for example. And 10 of them put things in their pocket, but 9 of them paid in the actual checkout, but one of them did not pay. If I ask to Vamba that which person did not pay for their product, does it work, or where do you see the challenges in such scenarios?
Well, I think it's always going to be possible to train the model on domain-specific data. For example, if you're only, for example, focusing on the problems like anomaly detection, you can curate a data set that are exclusively for anomaly detection, and we can have more samples related to these very tricky cases, such that the model can maybe better capture the temporal relationships between the first part of the video and towards the last part of the video. I think right now it also has some capacity to do that, but it's more trained on like a generic scenario. So I cannot guarantee the performance for that specific task. But the way that basically we are trying to, the model is trying to solve the problem is that it got access to all the video tokens or basically all the frames throughout this very long video, and it's tried to reason and find out the relationship between objects in, for example, the first half of the video and also the end of the video, and it's tried to create these connections, and then finally it tried to output some responses in natural language.